Good afternoon. I wanted to start today by letting you know that I've made a couple of updates on WebAssign, and your labs are due coming up a week from Tuesday. The reason why you have that long is because they take a while, so you should get started now. I have posted Lab 3. It has a lot of instructions for downloading a piece of software called Portal, which will help you access NovaNet. It is an old client-server software that has some centralized tutorials that we've built for you, and there's a lot of instructions for them. Please follow them. They pretty much should be okay. If you do have trouble, please post on Piazza if you need some help. Up at the top, it has some links. So this page has the instructions. Recommend that you print them out while you're doing the installation. By the way, you probably don't have to restart your computer. It's really just a small little client program, and I wouldn't restart. Just try to run it. So the instructions say to restart, but I've never restarted whenever I installed this, and it worked just fine. And it's a small program. It's not very big. It won't take up much room on your computer. You will need an internet connection. You can print out the Axiom list. So when you're doing proofs on the proofs tutorial on NovaNet, you'll use the same numbers that are on the Axiom list that's on the handout you have on your web page in class. And so you can just type the number of the rule that you want, and it will put it there. So you don't type the names of the rules, you type the numbers. So you'll have to have the sheet that has the numbers on there. You can also tab through the list, but it's kind of a pain. So I would have the sheet printed out. There's a sheet that gives you the function keys. So this was built before we had browsers with nice big buttons at the top that have arrows and things. So there is a back. Forward is pressing Enter, and hitting back is Control B for back. So next, they use the word next for enter. Back is for, like going to the previous place where I was before. Help is Control H for help. And stop is like if you want to quit out of the program, it's Control S. So this is the little table that I recommend you print out. There's a list of the proofs you need to work. So the reason I'm going through this is what I recommend you do is actually pull up this list. And work these problems on paper. Let me see if I can make this bigger. So it's a list of 10 problems. You have to do these 10 problems. So on the left are your givens. On the right are what you're trying to prove. It will take you a while to enter them on the computer, because what it's going to do is each line that you write on your paper, you will also have to enter it on the computer, and then it will check it and make sure that it's correct. So that's why you're using an older system, is because it's much smarter than WebAssign. So we've built a lot of intelligence into it, so it will check and see if what you have done is actually valid and allowed. And then it also detects when you're finished with the proof. And it does keep track of which problems you've done. So if you're in the middle of working on there and you log out for some reason, it saves what you've been doing so far. And it will save 2 versions of your proof. It'll save the first one that you do, and it'll save the latest one that you do. So if you work a problem and you're like, I want to go back and practice that, you have 2 choices. If you've already worked it, you can edit or you can work it again. If you work it again, you'll only be able to access that one. So you can only ever access one. We saved the first one just for research purposes, just to see what people do the first time they try things. So if you go back to a problem, you can hit edit, and it will bring up the problem that you had, and you can do that, or you can erase it and start over again. And like I said, it does save your progress. When you finish a problem, it actually has a menu that looks exactly like this, and it'll put the word done over here if you finished it. Or it might put direct or indirect, because you can, in the proofs tutorial, you can choose if you were going to prove something directly, which is the only thing we've done so far in class, or you can do proof by contradiction, which we're going to talk about today. So you can do both of those in there. I recommend, if you get stuck on a problem, to try proof by contradiction. I do recommend trying them direct, just because it's challenging and it's good for your brain. But if you have trouble, lots of students prefer proof by contradiction. And we'll tell you why in a little bit, but it's basically the way that computers do proofs, because they're pretty much guaranteed to work as long as the proof is provable. Okay, so these are your problems. Just so you know, in the past, people have problems with number 5 and number 10 and number 4. So If you have trouble on those, you're normal. Feel free to post questions on Piazza and we will answer them. Like I said, you're always welcome to work with other people, so feel free to work these with other people, but be aware that after you've written all these out on paper, it will take you a significant amount of time to put them into NovaNet and have it check it for you. Because every time you use a rule, you remember how we've been writing rules with P's and Q's? Sometimes when you work a proof, you're working with A's and B's. It's going to ask you, when you use a rule, which letter do you want to be P? So if I'm going to use modus ponens and I'm using it on A implies B and A, I'm going to have to tell it that P equals A and Q equals B. That's why it takes so long, because for every single rule you use, you have to map it to the rule in the system. It's good for you. It's just like broccoli. So try it out. It's actually very worth doing. Everyone who finishes these lets me know that it made it easy on the test to do these problems. So like I said, work them by hand. That's why I pointed out to you now, because you should go ahead and print these out and go ahead and start practicing the formal proofs. By the way, this material on logic proofs is the only material that doesn't have a good representation in your book. So this class is pretty much your best source of information on how to do these kinds of proofs. So feel free to watch the lectures again or look at the packets for sample problems. There are some sample problems worked. Also, I think at the end of packet 2, there's a study review guide for test 1, and that has some extra problems like all the way worked through several different ways. So be sure you're looking at your packets and at the test review and trying the homework problems, and you'll be fine on the test. Okay, so I was just pointing that out because you're probably going to look at this and go, oh my God, there's so much stuff to do. I'll go do it later. Okay, because I do that all the time. Okay, if you go do it later, just make sure you print out this list of proofs to work and then work them on paper when you have time, and then come back and do this installation stuff. You should install the software as soon as you can, but by the way, you will not be able to log into the proofs tutorial yet because I have to put all your list of names in there. So I haven't done that, but I will get to that hopefully today. If not, it should be tomorrow. So I'm hoping you can do them over the weekend. There are a limited number of login slots for the proofs tutorial. So working it early would be good. So I'll get your names up as soon as possible. I'll post a post on Piazza that when it's ready, so you can go log in. But definitely just print them out and work the problems first. By the way, because there's a limited number of slots, so we have free access to the software. People usually pay. So we're using a limited number of slots. So do it early. If it's coming up to the deadline, we'll probably extend the deadline. So don't freak out. If you're not able to log in, we'll extend it, and you'll have more time to finish it. But the sooner you start, the less likely it is that anybody else will be logged in at the same time as you. Okay? All right, so I apologize. I didn't realize that some of the assignments were not visible to you on WebAssign. So I'm going to fix that like immediately after class. So I didn't realize you couldn't see every single homework for the whole semester. So I'm going to fix that. So some of them are just like available tonight at 11:59 by some random chance. I think it's because this semester started earlier than last semester. So when I copied it over, it had the start date later. So I apologize for that. Okay, so you should see pretty much everything. And your TAs are going to add the test dates to the calendar on WebAssign in case you're using that to track, when you need to do stuff. So you'll be able to see it at the same time as you're seeing your homeworks. But pretty much each test is after 3 homeworks. So you got homework 1, 2, 3, test 1. Homework 4, 5, 6, test 2. And we have the dates all in Moodle. And I just did update a few of them because a few of them were like, one of them was on a Saturday accidentally and stuff like that. So yes.
Are the tests cumulative or are they?
No, the tests are not cumulative. The tests are only on those 3 homeworks. However, the final is cumulative. So the final exam is extremely hard, and it's like all the tests stapled together. So, yeah. Well, I don't know if you guys have access to like really, really old scores for NC State, but I have taught this class here. I taught it many years while I was a grad student. And our grade distribution was mostly A's and B's, 80% A's and B's for this class. And another professor who was teaching it came to our office one day and said, you must have a really easy class because your grade distribution is so good. Can I have a copy of your final? And he took it to his office and he started working it. And about 25 minutes later, he came back and he handed it to me. He said, this is hard enough. Okay. So the difference is that we give you lots of chances to make up for missing a homework or redoing a test or something like that. So it is hard, but you give you lots of tries. Okay, so with all that introduction, I just wanted to let you know that we did have that NovaNet set up there, and the dates on Moodle should be fine. By the way, any dates that you see on Moodle are guesses, and the real ones are on WebAssign, except for the tests. So the tests are already set for the whole semester. The 19th is the first one. I think the next one is approximately the 20th of October, whichever day happens to be a Tuesday or Thursday. And then the last one is the week before Thanksgiving. It's not the week of Thanksgiving. So the third test is the week before Thanksgiving. So Thursday before Thanksgiving. Okay, so today we're going to look at logical implications, logical equivalences, and formal proofs. And actually, I think we'll start with formal proofs and do some of the others after that, because we haven't done too much on formal proofs yet. So I'll do a little bit of that and then just do some review on the others. All right, so we started last time talking about formal proofs, and that they were basically ways of doing proofs where we didn't have to use truth tables because they get kind of tedious to do, and we want to be more intelligent about how we're actually writing a proof. So let me, actually I had a reason for pulling this up. I wanted to work one of the problems that were on there. So I often, as a little cheat code for you guys, I often work things in class that are on your assignments. So if you hadn't noticed that yet, make sure you take notes, because they're often exactly what you have to do on homework. So I'm going to work one of the problems that's on the proofs tutorial. Am I going to tell you what number it is? No. Okay. Actually, it's number 1. Just kidding. Okay, it's going to be, our first given is going to be A implies B. Then we're going to have C implies D. And we'll have not the quantity. A implies D. And we need to prove B and not C. Okay, you guys know that I'm lazy, right? So you can do this. It's totally fine for you to write given and just say all these things are given. We're trying to prove B and not C. Oh, sorry. Sorry about that. There it is. Okay, so today we're going to talk about proof by contradiction first. So a proof by contradiction is when I assume my givens, and then I assume the negation of the conclusion, and then I derive a contradiction. And that probably doesn't make any sense to you, so we're just going to do it, and then we'll talk about it some more. So, what does that mean? Negation of the conclusion means take the conclusion, copy it down, and then put a not in front of it. Now, you should be really excited, because this is the only time you could randomly negate something. I know you're super excited about that. That's right. Good. Thank you. Okay. Now, I'm pointing this out and trying to make it funny, because I don't want you to randomly put nots in front of anything. This is the only time you can do it, is when you write the word negation of conclusion. It means I am negating the conclusion. If you have anything else that you're putting in your proof, and you put, it's true, it's in the givens, and you put a not in front of it, then you've just put something false into your lovely mix of true things. And you're going to mess it up. So what we're going to do with a proof by contradiction is, how many of you have seen magic card tricks? Okay, so most everybody's seen them. And a lot of them have to do with red cards versus black cards, right? And almost all the time, the tricks have to do with the person who's dealing with the cards has already prearranged them. So half of them are one color over here and half are one color over here, and they already know something about it. And they're showing you things and making it look like, they have magic powers. Okay? Well, the magic power here is I'm going to start out, when I do a proof, everything in it I'm claiming is true. Okay? And that's why a direct proof, when I get to the bottom, when it has written on that line the thing I want to prove, then I'm happy because it's on my true list. Okay? Now, if I believe that I can prove this statement, then I believe it is true, right? So what should this statement be? It should be false. All right? So think about this as a deck of cards. These guys are red, okay? And this one's black because it's false. Now what I have to do is I'm going to shuffle my deck until I show that there's something black in there. And the only black thing that could be in there is this, because it's the only thing I've negated that I think should be true. So that's really how a proof by contradiction works, is that I have some true stuff, I throw the opposite of what I want to prove in there, shuffle it around until I show that something in there has to be wrong, and it has to be the thing I threw in. Okay? Now I posted an example of this on Piazza, okay, and hopefully it'll be a real example for you guys. How many people have ever had anybody give you any money to help with your school? Okay, excellent. Most people. So this example should be real for you. All right? Suppose this person gave you some money to help you with school, but they were maybe worried that you're going away and you've never been away from home before and you're going to spend all your money on beer or some other such thing that you shouldn't be spending your money on, like a car or whatever. And they want to be sure that you're actually spending your money on your education. So a direct proof that you are spending your money on your education would be what? A receipt, right? Or they can pay directly for your bills, right? You could give them receipts for your books, receipts for your food, for your housing, for your tuition, all that stuff. Okay, do you want to do that? No, it sucks, right? Receipts are terrible. I hate them. Okay? They're like, tax forms and stuff. It's not good. Okay? So, what do you normally do? You call Grandma and you say, Grandma, I got all A's. I couldn't have possibly spent my money on beer. Right? That's what we would call an indirect proof, okay? The indirect proof is, if I get the cash and if I were to spend it, suppose I did spend it all on beer, would it be possible for me to make all A's at my challenging engineering major? The claim is no. Okay? So you want to make the case that there's a contradiction here. I couldn't possibly have spent all the money on beer and also get all A's at the same time, so therefore I must not have spent all the money on the beer because I have the A's and here's my report card. Okay, so, maybe you guys have already figured out the financials and you can buy plenty of beer and also make A's. Good for you, but I'm going to assume that you can't do that. Okay? And maybe you think you can do that because you haven't turned any homework in for this class yet. So next week you can't do it. Okay? So, we do it all the time. We do proof by contradiction all the time. Right? Whenever anybody accuses you of not doing something, you're like, I did it, here's some evidence. But it's usually a proof by contradiction. So watch yourself for a week and see if you use any proofs by contradiction. So proof by contradiction is where you say, well, if I did that, then it would have been this way, but it's not. So that's a contradiction, so I didn't do that thing. Okay, we do it all the time. So how we literally do it with our with proofs for computers is we write down the opposite of what we're trying to prove. We end it with all the stuff that we know is true because it's a hypothesis, and then we're going to try to combine it. So what I like to do is mark the negation of the conclusion with the dollar sign. And now you're probably like, wow, what are you doing there? So remember I told you this is like I have a deck of cards. Some of them are red. This one is black. I want to show that it's black. Okay? The way I'm going to show that it's black is I'm going to recombine them all until I get a contradiction. So I have to get something false. So I have to actually literally get something that means zero, like P and not P. Or A implies B and not the quantity A implies B. That's definitely false, right? Can't argue with that. Those are contradictions. Anything ANDed with its opposite is a contradiction. That's rule number 26. So if you see rule 26 all over your homework, that's what it's talking about, is that if you have two things ANDed together that are opposites, we always get zero. That's what that means. So I'm labeling this with money because if I want to get the black card out, I have to use the black card, right? So if I have a deck and all I'm doing is playing with the red cards, am I ever going to pull a black card out? No. This is the black card. So I have to mix it with the red ones in order to get the money out. So I like to call this the money because this is like the store. I'm going to spend my money at the store to get my black card. All right, how am I going to do it? Well, first I have to get rid of this knot on the outside. And we talked about De Morgan's last time. That helps us distribute knots across ands and ors. So let's do that. So we should get not B and not C if I don't skip any rules. And that's from line 4 and De Morgan's. And I'm going to cross this out because I've used it. It doesn't mean I can never use it again, but just to help me pay attention to where I am, I'm going to cross it out. And if I derive it using the negation of the conclusion, I'm going to put a dollar sign next to it, just so I know I'm keeping track of the fact that I'm going to use something that came from the negation of the conclusion. You look like you have a question. You're right. Thank you for checking my mistake. So we had B and not C, and then when we negated it, we should have not B or not C. Good checking. Okay. Now we're going to get rid of that double negation. So we have not B or C from line 5 and double negation. And these are still from the negation and the conclusion, so I'm going to keep labeling it like it's money. Now, does anybody know what not B or C is logically equivalent to? B implies C. Good. So that is from line 6 and the implication rule. All right, so now we've actually sort of applied De Morgan's and we've gotten rid of as many symbols as we can with this, right? There's nothing else I can do to this by itself without starting to combine it with something. So now I need to go to the store, which is my givens. And I want to see if I can combine this B implies C with something. And I'm going to keep doing that repeatedly until I find two things that are opposites. So I got to be watching out all the time for two things that are opposites. Did you have a question? Okay, any questions so far before I slide this up? Yes.
Are the givens always consistent?
Are the givens always consistent? I will never give you a problem when the givens are false. Is that what you're asking? Yeah, so we won't, so what we're practicing in this class is how to prove things that we know we can prove, or at least we think we can prove. So I'm not going to give you something that shouldn't, that if I ended those two things together, I'd get a contradiction. So I don't have any problems like that. It's possible for you to run into those problems. If you did, then I would work the problem again and make sure, and then you won't run into it in this class, but if you ran into it somewhere, if you feel free to bring it to my office and I'll check it for you. Okay, so what do you think we could get? So what's the first thing you see? If I combine B implies C with something, what can I buy at the store? I can get A implies C. So this is still somehow derived from my negation of the conclusion. So that was from line 1 and 7. And hypothetical syllogism, remember that was the transitive rule, like less than or equal to has. Now we're going to repeat that process. So we have our A implies C money. We need to see what we can buy. We've actually kind of already used A implies B, so I'm going to put a check next to it. Again, you can reuse a line. I'm just marking which ones I've used just because I want to use the other ones first. If I've already used it, I want to try the other ones that I haven't used first. So now I think we can actually use the same rule with line 2, right, and get A implies D. So we've used line 2, used line 8. This is still coming from the negation of the conclusion. Does anybody think we're almost done? Raise your hand if you think we're almost done. Good. And most of you see that we're almost done. So what is the line that shows us that we're done? So 3 and 9 are what? They are opposites. So now all we have to do, so this is a funny, weird thing that we have to do. We have to put them next to each other. So it's easy to see that they're opposites. So that's the next thing we absolutely have to do. We have to say the quantity A implies D and not the quantity A implies D. And that's from lines 3 and 9. And the rule is called conjunction. And it's weird to have a rule for this, but basically we have it because everything in a proof is anded together, but we usually keep them on separate lines. So if we put them together, we say conjunction. So if I know two separate things are true in two separate places, it's like my friend over here told me that this car was red, and my friend over here told me that it was a Porsche. I put them together, I get red Porsche. There's a rule for putting those two things together from two different sources. So that's what conjunction is. It's the funny Latin word for and. Have you ever heard of the conjunction junction from the... Yeah, exactly. That's what it's from. Yes? Yes, you will always do a conjunction, and then you'll do one more thing, which is to claim that there's a contradiction. So that's the last thing that we're going to do. We're going to have another line that says contradiction. And on your homeworks, it actually says Rule 26, but you don't have to write it on your homeworks. Like if you handwrite something on the test, you don't have to put Rule 26, yes.
In our web assignments, when it asks for the rules we use, do we say like Rule 27, or do we say...
Just type the word. Type the word. I don't think I put the table of numbers in there. But if you use my abbreviations like HS and DN and DM, so my abbreviation actually is DM in the system and IMP. So all these you could type just like that. Yes, you can type the whole word, or you can type an abbreviation like a 2-letter abbreviation or 3.
So all of the rules that you have on the right, those are all the axiom list?
Yes, these are all on the axiom list. So hypothetical syllogism is in the first 10, and the first 10 are all logical implications that only go one way, and the rest of them are equivalences, like things I can substitute anytime I want to. So double negation and De Morgan's are logical equivalences, right? So I can go back and forth in between. But once I've derived, like say on here, I've derived A implies C from A implies B and B implies C, I can't go backwards. So just because I know A implies C doesn't mean I can know the other stuff. So when I'm working a proof, I can go forwards, but I usually can't like look at something here and then derive something that came earlier. So I can look at the list and see what it is, but I can't derive new stuff from it.
So basically, the way that this works on the larger scale is that you take your proof and you negate it, and then you say, if the proof was true, I've now made it false, and then you prove that it's false.
Right.
By finding the...
That's right. Yeah, so what's your name? Ben was just clarifying that the process we've just gone through is when we're trying to prove something, this is called our conclusion. So when we did the proof, we assume this is false, right? And we stick it in, well, yeah, we assume it's false. We stick it in here, and then basically when we get to the bottom and we show that there's a false, the conclusion naturally is that the thing we stuck in there must be false, right? But if I put another not in front of this, I get back the conclusion. Right? So if line 4 is false, then B and not C is true. So we don't have, when we do a proof by contradiction, since we put in the negation of the conclusion and we get a contradiction, the assumption after that, like I don't have to write a sentence that says, because I have a contradiction, the negation of the conclusion is false, so therefore the conclusion must be true. That's what it means, but I don't have to write that down because everyone who reads these kind of proofs knows that that's how they work. So once you have a contradiction, you're done. Yes? Yes, you will have to do 4 through 11 on your own. That is exactly why I tell you to print out the homeworks and do them before you go to WebAssign, because WebAssign has some fill in the blanks. But that is also the reason why we have the labs, the deep thought, justified thought, deep thought, and the proofs tutorial, because those are ways where you get to work the problem, like 4 through 11 on your own, but the computer's checking it for you. Because otherwise, if you had all those papers and turned them in, it would take us forever to read them all and get it back to you. And so that's why we're trying to give you different tools for giving you the feedback on different ways to do it. So WebAssign is a quick way to get feedback, but it's not very smart. The other ones are smarter, but they require a little bit more work on your part to enter the answers. So the reason why you have these fill-in-the-blank proofs on WebAssign is just to get an idea of like what a proof looks like and what the rules, individually do. So it's practice. So if you need more proof problem practice, do the ones that are on the proofs tutorial. Take the ones that are even on WebAssign and like erase cover part of it and see if you can do it. You'll be amazed that your brain will totally forget like what you just did, and you can use that same problem again. Or if you're doing a direct proof, you can do it by contradiction. Or vice versa. If you have a proof by contradiction somewhere, you can do it by direct proof as a practice. Any questions about this problem? Now, there are many, many ways to solve a proof. After you start working some of them, you'll probably ask me something like, how long should my proof be? And the answer I like to give you is similar to the answer that Abe Lincoln gave when somebody asked him how long a man's legs should be. He had really long legs because he's really tall, right? His answer was long enough to reach the ground. My answer to how long should a proof be is long enough to get to the end. Now, that doesn't mean that you should spend forever. If you are working a proof that is assigned in this class, you should not work on it for longer than 30 minutes. If you are working on it for longer than 30 minutes, you have probably copied something down wrong and made a mistake. Because we don't have anything that should take longer than 30 minutes. You need to get some help if you're taking longer than 30 minutes. Okay? So if you're working pretty much any problem in the class and you're taking longer than 30 minutes, you need to get help. So go to Piazza, go do something. The other thing is, if you have a super long proof, like if you have anything that's 30 lines long, you definitely did some extra stuff you don't need. There's not a single proof I will give you that can't be done in 25 lines. I don't mind if you use 30, but you're wasting some of your time. So that's up to you. I'm not going to mark it wrong, as long as it's correct. But it won't be wrong for being long. Okay, so let's do this by direct proof. So if I do this by direct proof, what I'm going to do is I'm going to look at what I'm trying to prove, and then I'm going to try to find something in the givens that looks as close as possible to that, or at least gets me some of the variables that are in what I'm trying to prove. So the variables in what I'm trying to prove are B and not C. They are ANDed together. So you guys saw that we just did conjunction at the bottom of our other proof. So one possible thing I could do is get B by itself and get not C by itself and AND them together. There might be some other ways that we can get this. There are many, many ways to do a proof. And there's not just one correct way. So when I look at this, I say, okay, well, there's a B on line 1. And I like that, but I don't like that there's that A implies thing on there. I want to get rid of it. But the only other place where I see any other A's on here is line 3, and there's a disturbing knot on the front. But I can treat that one just like we treated a knot around an implication the other day, right? We can change that implication into an OR, and then do De Morgan's on it. So let's do that. So we use the implication rule. So by the way, most abbreviations I write down here are ones you can type in WebAssign, because I have put them in. All right, so now we're going to do De Morgan's. Now, I'm not labeling anything with money because I'm not looking for a black card. I'm not doing proof by contradiction. I'm doing a direct proof. But with that in mind, I'll probably never use 4 and 5 again, or even 3, right? So I'm trying to make 3 more manageable. That's what I'm actually doing. So now I've got A and not D. Now, anytime you see an and a proof, the whole reason why I started dealing with line 3 was to get A by itself, right? So let's get A by itself. So let's simplify. So 6 and simplification will give me that. And I believe I mentioned simplification the other day. But I may not have. Did I? Raise your hand if I mentioned it, if you think I mentioned it. Okay. So if I have an and statement, and I say I have an apple and I have an orange, it has to be true that I have an apple, right? Because the and won't be true unless both parts are true. So anytime you have an and statement on the line of a proof, you can simplify to one of the sides. Now, technically, your computer thinks that simplification means you can only simplify the left side, because the rule only says that if you have P and Q, then you can derive P. Does anybody know why we can also derive Q? Because and is commutative, which means it doesn't matter which side the letters are on. So just like multiplication, multiplication is also a commutative. So I always had a hard time remembering what these things mean, even though I was a double math major. So commute, the word commute means like change places. So like even when you're commuting to work, you're changing places, right? So think of something that helps you remember things. So it's commutative that lets you do that. So technically, if I want to simplify not D out, I'm going to have to commute line 6. So here's a little note, by the way. The NovaNet Proofs tutorial will let you skip this, and it will let you skip this. The Deep Thought tutor will not let you skip double negation, but it will help you do commutative, because if you want to simplify from A and not D, it'll ask you, do you want to simplify the left or the right-hand side? So there's a little bit of trickiness with each of the tutors, which things they've implemented. So the Deep Thought tutor was written by a philosophy professor, and the Proofs tutorial was written by grad students in computer science and myself. So they have different philosophies behind them. Deep Thought is graphical. The other one is textual. So, but I built in a bunch of stuff to let you skip things. That was back when I was a grad student. So I'm going to simplify line 8 to get not D. Okay, I just did that because it was an and I was simplifying. So I might as well simplify the other side too, but I might not need it. I was purposely doing this so I could get A by itself. So now let's get A by itself. We used A. Let's use it with line 1. And with A and A implies B, what do we get? We can get B. Awesome. So from 7 and 1, we can get, we used modus ponens. That was the if it rains, I'm going to get wet, and I know it's raining rule. And from not D, let's see what we can get from that. So it looks like I could do something with line 2. So that basically not D says that I'm not getting wet. So what do we know? It must not have rained. So from line 9 and 2, that's a new rule we haven't talked about before, but it's called modus tollens. And it's almost like modus ponens, except when in modus ponens I know something about the hypothesis, right? I know that it's true. And in modus tollens I know the conclusion is false, so therefore the hypothesis must be false. So I call modus tollens is the I didn't get wet rule. I didn't get wet, so therefore it must not be raining. Okay? And the modus ponens one is it's raining rule. Okay? Okay, so isn't it amazing that the thing I want to prove is B and not C, and I have B and I have not C? Yay. So we're done. So on line 12, we can put B and not C from 10, 11 in conjunction. So how many rules on here were new for you today? Okay, so 2 or 3. Not too many. And commutative's easy. You already knew it from math, right? And simplification was easy because we know that ands can be simplified, right? And conjunction's easy because that's like we can make ands out of 2 things that are true. So we only added some easy stuff. The hard one we added was modus tollens. But it's not too hard because we already learned modus ponens really well, and it's very similar to that. Okay, so the reason why I pointed that out is we just did a whole proof without having to look at the axiom list, right? I mean, you have me, but you will have me on the test, but I might not say anything. So you may come up and ask, if you're reading a question that's not clear, you may come up and ask. And I will usually answer that, but I'll answer it by writing it on the board because I don't believe in doing anything that's not fair to everybody. That is why, for all your tests, if you look on Moodle and you click on the test, there's a practice test there, okay? So you don't have to be in a fraternity to get the old tests. They're right there, okay? We know that you guys do that stuff. So anyway, the reason why I mention that is doing a proof is not the process of writing down your problem and looking at the axiom list. What I want to do is make wishes. Did you notice I was making wishes every time I was doing something? So I looked at what I was trying to prove, and I'm wishing that I'm wishing this was already somewhere in my proof. So I look for it, or I look for something close to that. And then I figure out, okay, I want to wish that I found that A implies B, then I wish that the A implies would go away. And then I find something that helps me get rid of the A implies. Then you can go look at your axiom list to see if there's something that helps you combine those 2 things, because then I'm looking for something specific on the axiom list, right? I'm looking for something that has an implication and, gets rid of the left-hand side of something. Modus ponens does that, right? I have an implication and I somehow zap the left-hand side of it. So I knew that I wanted just A by itself. So that's what I want. That's the process I want you to do, is make a wish and then go see if the axiom list has it. This is how we write programs, right? I want to print something out. Let's see if there's a print function. Oh, there is. Lovely. How do I use it? That's what you're going to do. So, but we don't sit there with the manual, the Java docs, and go, I got to read everything before I can start working, right? We start working, we make wishes, we look for things we need. Okay, so we did that 2 different ways. Now, there's many, many ways to do a proof, and I'm going to show you a really cheap method for doing a proof by contradiction. So some of you are going to like direct proof better than proof by contradiction. Does anybody already know that they like direct proof better? Okay, we got 1. Good. 2, 3. Okay, I'd like you guys, come see me in office hours. Maybe I'll give you a job. So if you like direct proof better, that means you like to figure stuff out. And proof by contradiction feels like a magic trick. Okay? And it does. That's how it feels to me. Proof by contradiction feels like, you didn't actually show me how to do it. You just showed me that you couldn't do it. Okay? I don't like that. So, that's right. So we're taking a discrete math class so we can learn methods for doing things, and I'm showing you different methods. Now, the thing I told you, actually, this proof by contradiction method is how most computers actually do proofs for stuff. So if I want a computer to prove something, it will do proof by contradiction. It's called resolution, and it's an algorithm that it uses. It's exactly the algorithm we used, which is negate the conclusion, distribute the not, simplify as much as possible, take the pieces, combine them with the givens. That's exactly what they do. Do it until you get a contradiction. Okay? So that's a good algorithm. Yes? That's a great question. So the question was, is there sometimes when one method will work and the other one won't? Both of them will always work for anything I will give you in the class. So sometimes there are things that we can prove by contradiction, but we can't prove them straightforwardly. And that is a great question. So I'm wondering if I should give you the one example that we can't do by direct proof, because it might blow up your brains. Do it? Do it? Okay. Okay, I'm going to do it. But if someone kills me, you guys know. You guys know that you asked for it. Okay. Yes? But for this class, both will work. So I'm going to give you an example of one problem that you cannot do by direct proof. But for everything in the class, both will work. Now, if you're doing something you can't get it by direct proof, do it by contradiction. Almost everybody can do every proof with proof by contradiction. So I like to try with direct proof, and then if you spent 30 minutes, try it by contradiction. Also, start over on a clean piece of paper, because you might have a random mark on your paper, and maybe you thought there was a not somewhere, and there's not. So that's the other thing. After 30 minutes, do not erase on the same piece of paper. Now, if you guys are anything like me, you use up every little bit of every piece of paper in the front and the back. Okay? Don't do that. Okay? Here's how you can do it for your discrete math homework. Take your scrap paper that you already have a mess on. Okay? Start writing the proof on there. If you mess up, get another one. Okay? It's cheap because those stray marks will mess you up. Okay? So don't be cheap with your paper, because you don't have to use that much, because we don't turn things in on paper, right? So for the little bits, just use as much as you need. Start over clean. And then double check when you copy the problem down that you copied it down right. Because if you're having trouble, something went wrong. Okay, so what is this weird problem that we can't do by direct proof? It's called the halting problem. Has anyone heard of it? Yay, 2 people, 4 people, 5 people. Excellent. Okay, the halting problem is a classic computer science problem, and people who are really nerds in computer science really like it. And the reason why we like it is because we hated it until we figured it out. And then we like it. Okay? So I had to deal with the halting problem when I was a freshman, and I accidentally took a senior level class that was also cross-listed with grad class. Don't do that. Okay? Use an advisor to help you pick your courses. So I took the graduate finite automata computation theory class, and I had not had discrete math yet. Don't do that either. Okay, so did I pass? I made a B, and I was happy. And it was one of my 2 Bs ever. And I remember, right now, I can physically remember sitting on the floor, feeling like my brain exploded, doing my homework from that class. And it was on the halting problem. Okay, so the halting problem is, here's the question. Can you write a program that takes another program, P, as input, and output, whether or not P will stop? This is like those, you have 3 people and some of them lie all the time and some of them tell the truth and all that stuff, only it's harder. Yes? I thought I heard a question over here. No? Yes?
Does stop mean it encounters an error, or it just doesn't go on forever?
It means it doesn't go on forever. So it doesn't get hung with an infinite loop, basically. Okay. Does anybody think they can write this program?
No.
Does anyone think it's possible to write this program? Yes? Okay. I'm not going to give you a job because no one has been able to write this program. Okay? So this problem is incomputable. It is not computable. Okay? Say, for example, let's call this problem H. Okay? What happens if I do that? What if I run H on H? Huh? There's a program H. It's a program. It could be the input to H. What was the question? Doesn't your what? Doesn't your input need an input? It's just reading the program, so it doesn't. No, it's just a program. So it's like text. So I didn't prepare a lecture on this. We will do some more on this, but this is a non-computable problem. There's not an algorithm for this. So no, you can't do this one by direct proof. But people prove that this is not possible by contradiction. So usually the things you can't do by direct proof are things that actually aren't possible. So you prove that they are not possible by contradiction. Because you would say, if it were possible, then we could do this. And we know we can't do this because someone else already proved that we can't do that. Okay? So good question. But I'm not going to do more with this because it'll be off the top of my head and it'll be wrong because this is complicated stuff. So I will prepare a lecture on it because it is fun and I was going to do it anyway. So we'll have some more on that. But we're going to do a couple more proof things here. Okay, so this is fun, and we're also going to look at the traveling salesman problem and a couple of other classic cool computer science problems. So thank you for asking that question. Okay, so I was going to teach you a cheap and easy way to do proof by contradiction when you hate proof by contradiction. Or if you just happen to be really good at direct proof and you want to take advantage of that. Okay? So we just did this direct proof, right? That's the one we did. You already have it on your paper. I need to write it down. Now, the thing I put into a proof by, this is a direct proof, right? There's no negation in the conclusion. There's no conjunction that puts two things that are opposites together. And there's no line that says contradiction. So the minimum requirements for a proof by contradiction is that I have to have those three things. So I can take this proof and put those three things on the bottom. Right? There's no rule that says I can't. So we say 13, not the quantity B and not C. That's the negation of the conclusion. (14) B and not C, and not the quantity B and not C. That's for 12 and 13 and conjunction, and 15 is a contradiction. Yay! So Dr. Barnes said I had to do a proof by contradiction. I did a direct proof, and I put the stuff for contradiction on the bottom. So for the three of you who like direct proof better, here you go. Any questions about that? This is not really a cheating method because direct proof is harder than proof by contradiction, except for some few people. So for most people, direct proof is harder. So this would be like going around your elbow to get to your nose. So, whichever one works for you. Okay, so let me talk about a few more rules that we haven't talked about yet, just to make sure that you're familiar with them so that when you are making your wishes on your proofs, you know what you should wish for. Okay? So I believe that I mentioned that implication acts like less than or equal to. Yes? So let me just remind you that if we have P is less than or equal to Q, and Q is less than or equal to R, then P is less than or equal to R. That was our transitive property if we're in math, and it really means the same thing in logic, but we write it as this in logic, and we call it hypothetical syllogism. But we can do other stuff with less than or equal to in regular math that we can also do in logic. So the reason why I write this is that implication has the same truth table as less than or equal to when we're talking about binary, which that's all we talk about with implication because we don't have regular numbers with implication. It looks like there's a question over here. You guys got a question? Thank you. You should have asked me sooner. I don't know. I was just doing consecutive letters. There you go. I told you guys if you're closer to the board, your brain doesn't work as good, right? Okay. So you're good. Thank you for checking my writing. That was crazy. Okay, so P implies Q is logically equivalent to less than or equal to. So you can make a truth table, they'll come out the same. So anything you know about less than or equal to, it's also going to work with implication. So one of the things we actually know about less than or equal to is we can add the same thing to both sides of less than or equal to, right? We can also multiply the same thing on both sides. So we can do the same thing with implications. So if I have P implies Q, I can and or the same thing onto both sides. And this is on your axiom list as one of the implication rules. I think it's like 36, but I apologize, I don't know the number off the top of my head. What? Then it's probably not 36. It's one of the implication rules. I'm sorry, I don't remember the number. Okay, there's another one So we could also do ands, right? I can and the same thing on both sides and the same thing will happen. We could prove these by truth table. Does anybody really want to? You trust me. Thank you so much. Okay, you shouldn't trust people. Computer scientists prove things for themselves. But we have an axiom list. It's on there. It's fine. Okay. The next thing, though, is, so those are just some things you should know. Those are on the axiom list. So if you see something and you're like, wow, I wish there was an and or on both sides of that, you can do that. Okay? Another thing is, if I have, let's just start on the new sheet. If I have two implications, it's just like having two less than or equal to's. And if I add the left-hand sides and I add the right-hand sides, do I know anything about comparing those two numbers? Well, if I add these little things, and each of them is smaller than these other things, shouldn't I get a smaller sum on the left than on the right? Do you think this will always work? Yes, it will always work, because I have not multiplied by a negative number. That's the only thing that will mess it up. Okay? So I can add or subtract the same thing from both sides of an implication, or I can combine it with an implication that's in the same direction with pluses, and it will still work. And I can also do the same thing with times, as long as I don't use negative numbers. Why can I not use negative numbers? Because it flips the less or equal to. So I can't just multiply both sides by negative. So the same thing works with implication. I can't just negate both sides. It will not work. Okay? So don't do that. But what does this mean? So this means actually what we did over here is 1 plus 5 less than or equal to 3 plus 7. And the reason why that worked is because the 1 is less than or equal to 3 and the 5 is less than or equal to 7. There's nowhere I can get extra pieces that will make the left-hand side grow bigger than the right-hand side. Right? Because all the pieces were smaller on one side than all the pieces on the other side. And I can match them up. And we're going to later talk about a thing called diagonalization. If I can match up all the things on one side with all the things on another in a similar way, I can do group comparisons. And we'll call that diagonalization, but we're not going to do that today. So all we're going to do, though, is say that we can do A plus C implies, A or C implies B or D, because or is just like plus. By the way, I'm not going to count off if you use pluses and times, but when we're doing logic proofs, I want you to use the and or symbols. And when we're doing circuits, I want you to use times and plus, because that's what we do. When we do logic stuff, we use logic symbols. And when we do engineering stuff, we use math symbols. And why is that? These are conventions, okay? It's like when in Rome, do as the Romans do. So when we're doing logic proofs, we do as the Roman logic proof people do, okay? And when we're doing engineering, we do like engineers do, okay? You guys have to do both in this class. So in a way, this is like a language class. You're learning how to say this stuff basically to Dr. Barnes, but I'm telling you how to say it to other people too. So if you go talk to logic people, philosophy people, you can write your proofs the same way they do. When you go talk to engineering people, you can write your reductions the same way they do. All right, good. So now, this is called constructive dilemma. I don't know why it's called a dilemma, because I'm not confused about it. Yeah, maybe it's like two lemmas, and lemma is a word for a little teeny proof. So constructive means I'm putting together, right? So I do abbreviate this with CD, and I put an or after it because we used it with or. You can also do it with and. Now be real careful if you do this and don't mix up where the things go. Make sure the left-hand sides are on the left and the right-hand sides are on the right, because if you mix them and cross, it's not going to work and you won't be able to prove it. Constructive dilemma is the most powerful rule. You won't use it a lot, but when you need it, it's the only thing that will do the trick without having to do 10 other things. Okay, so it's a really cool rule. Now, let's go back to the proof we did before and see if constructive dilemma would make our lives even happier. Now, if I look at this, I'll say, oh, I need B and not C. Well, there's a B there and there's a C on the other side. Well, implications can be changed, right? The order can be changed if I do what? So contrapositive is when I want to reverse the order of an implication. So if I say, if it rains, I'm going to get wet, that's logically equivalent to saying, if I did not get wet, then it must not have rained. Those are always logically equivalent. When one thing happens, the other thing always happens. And I'm going to do a really quick proof of that right here. So C implies D is logically equivalent to not C or D, right? And D implies not C is logically equivalent to not D or C. I'm sorry, or not C. Are these two things the same? Yes, they are, because not D is the same as D, and not C is the same as C, is the same as not C. And they're ORs. So those are logically equivalent. They're always the same. So I want B and not C. There's a B on the right-hand side of line 1 and a not C on the right-hand side of line 4. Right? So I could use constructive dilemma to get those guys together, and I want them together. So let's do that. So in order to do it, I have to also get the left-hand sides together, and I need to use which operator? And. So I'm going to do A and not D implies B and not C. That's going to be 1 and 4 and constructive dilemma with an and. You don't have to write that part. Okay, so this is nice. Now I want to make a wish that this stuff will go away. And that stuff will go away if I can cancel it out somehow. And there's some variables that look a lot like that on line 3. Right? So line 3, well, it doesn't have an and on there, but it's got a very promising not outside of an implication. Remember, the implications are ors. A not outside implies that it's going to turn into an and. So let's do our implication rule on it. So we get not A or D. By the way, there is a rule that will take you directly from not an implication to an and you can use that, but I never use it. Yes? It is. Yes, but I never skip this step because the ands and ors are so similar looking that when you're writing a lot of stuff and you're taking a test and you didn't sleep for 10 hours, it all gets all jumbled. So I always, always, always convert an implication to an or and then do De Morgan's. And I've been doing this for years, and I'm not taking a shortcut. So you can do what you want, but I'd recommend sticking with one method. Okay, so that was from line 3, and we used the implication rule. And then 7, we're going to do De Morgan's, and we're going to skip double negation, so we're going to get A and not D was 6, and it was De Morgan's, and technically double negation 2. Right? And then, wow, that's cool. That's just like the left-hand side of 5. So our last thing is just going to be to conclude that B and not C is true because 7 exactly matches with the hypothesis of 5, and modus ponens tells me that if it's raining, I'm going to get wet. So I'm writing down that I got wet. And 5 and 7, and modus ponens let me do that. So is this a better proof? Raise your hand if you think yes. Raise your hand if you think no. Do I care? Raise your hand if you think yes. Raise your hand if I think no. Good. I'm glad that you know that I don't care. So, I don't care because you have your own brain. You have to pick which rules work for you. If they make sense for you, you've got to use those. So, use what makes sense to you. I'm showing you the different things that I think are useful. So let me remind you a couple of other rules. And And I apologize sometimes if I seem like I'm telling you something and I think I've already told it to you. There's two reasons for that. One is I have taught discrete math since 1996. And I believe I have already taught everybody discrete math. But I haven't. Because new people keep getting old enough to learn it. The second reason is I'm teaching another section of this class. And I do it every day. And I'm like, I'm not sure what I said in which class. So I have notes and I go over them, but sometimes I forget. So I apologize if I tell you something twice. So just remind me, or if I'm assuming that you know something, just let me know. All right. So a couple of other rules. You know, I like to draw pictures. I wanted to be an artist when I was a kid. You can tell, right? I happen to like things that look like kids' drawings. So if I tell you I have an apple or an orange, and then I tell you I don't have an orange, what do you know? You must have an apple. It's pretty obvious, right? That rule is called disjunctive syllogism. I like to call it the apple-orange rule so I can remember which one it is. Now, the word syllogism, I think I mentioned, means a thing that's true. And disjunctive is a word that means or, like just disjunction, function, what's your disjunction, junction, what's your function? So that's what I use to remember the ands and ors. So disjunctive is about or, syllogism is a true thing about ors. So if I tell you I have an apple or an orange, I tell you I don't have an orange, or if I tell you I don't have an apple, I must have the other piece of fruit. So how do we write that with our letters? P or Q, and not P, logically implies Q. Does this remind anybody of modus ponens? If it does, then you're like me and you think everything's the same all the time. And that's good, because you'll probably be able to switch between things in your proofs and get them done quicker. Okay, the reason why I ought to remind you of modus ponens is I've got a statement, an expression with two things in it. I've got another one that's canceling out one of the terms and getting one of those. So actually, this is basically the same thing as modus ponens, because in modus ponens I have P implies Q. And we know P, it's not exactly the same. But P implies Q is logically equivalent to not P or Q, right? So P happens to be the opposite of the one that's the hypothesis. So disjunctive syllogism and modus ponens are doing the same thing. Which one do you like better? Do you like modus ponens better? Do you like disjunctive syllogism better? Yeah, I knew that. You like it better because it seems easier. Okay? You should not try to use disjunctive syllogism that much in your proofs. You should try to use modus ponens. The reason is there's more rules that let you do things with implications than there are rules that let you do things with ors. And you want to use the stuff that would get you the most things. So try to do stuff with modus ponens, hypothetical syllogism, instead of converting everything into an or. We still have 5 minutes, so don't get up yet. Okay. We did contrapositive, so contrapositive was, just to reiterate that, if we have P implies Q, that is logically equivalent to not Q implies not P. This is the only thing that we can do with an implication. You cannot apply a not to an implication. If you do, it changes into an and. Okay, so that's called contrapositive. When you are working deep thought, you will need to know the addition rule. You will probably not need it on most of the proofs that I give you, but philosophy people like to add random stuff to their proofs. So, if I tell you that I have brown eyes, then I can also say I have brown eyes or anything else in the world, and it'll still be a true statement, right? Because ors preserve truths. So that's what the addition rule is you can add any BS to anything you want as long as the first thing is true. Okay? So P implies P or Q is how that's written. So that means if you have something that's true, then you can OR any old thing you want with it. And that can be useful, right? So if I tell you to prove B or C, and you can figure out how to prove B, but there's not even any C's on the page, that's okay. Use addition rule. Just put or C on there and you're fine. That's because B or C or P or Q is less true than P, right? So if P is false, or it could be more true, but if P is already true, then P or Q is definitely going to be true. So I don't have to know anything about Q at all to be able to OR it on anything I want. Okay? So you'll need that sometimes, but not for anything on the proofs tutorial or the homeworks. What else will you need? We've done hypothetical syllogism. We've done modus ponens. We've done modus tollens. We've done contrapositive, De Morgan's. We've done addition. We've done simplification. We've done conjunction. Those are all of the main things you'll need for proofs. So most of these have something in common. So all of these, except for De Morgan's and conjunction, are logical implications. So these are things that, if I know the left-hand side, I can get the right-hand side, but I can't go the other way. All the other rules that we've talked about are logical equivalences. So these, De Morgan's and conjunction, are logical equivalences. Actually, it's just De Morgan's. So we have some other logical equivalences like double negation, implication. We have contradiction. That was the P and not P is logically equivalent to 0. We also have one called tautology. What is the simplest way to write something that is a statement that is always true? P or not P, that's right. So P or not P is logically equivalent to 1. So that's called the tautology rule. You won't hardly ever use it. And then we did some idempotent rules, right? So those weird ones like P or 1 is logically equivalent to 1 and so on. P or 0 is logically equivalent to P. So those are the rules you'll need, but you won't need those too often. So even though there's 33 rules on the axiom list, there's not 33 things on this page, right? And you're not going to use most of them most of the time. So you're going to use these. They were on the top of my head, which means you're going to use them. And you're going to use these, implication and double negation. The other ones, you'll use them sometimes. Constructive dilemma, you'll use sometimes. It's not something that you use all the time. It's also a logical implication. All right, thank you very much. We'll see you next time.